First of all, you have seen so far, what you have seen is the closed string theories and the 2A and 2B superstring theories. Sorry, my handwriting is, but you can understand, right, more or less, even though the spelling is not correct. It doesn't matter. So these are the closed ones. And Clifford also talked about the open type 1 string. And this was a so these are the string theories that we have seen so far in this, since last week. These two are the closed superstrings, and they have n equal to 2 supersymmetry in 10 dimensions. N equal to 2 Suzy, D equal to 10. Whereas this is open string, so half of the supersymmetry is broken because of the boundary condition. Because as happens, why is there n equal to 2? Because in closed string theory, you have left moving sector and right moving sector, and they are kind of independent. So there is one supersymmetry which comes from the left moving sector, and another supersymmetry comes from the right moving sector. That's why it's n equal to 2. But in open string, because of the boundary conditions, the left and right are identified, right? So you only have actually the diagonal subadjectives. For this n equal to 2, it reduces to n equal to 1. So here you get n equal to 1. N equal to 1, of course, is much more interesting from the point of view of phenomenology. The reason is that here, at least this was the case in the old time before the discovery of deep brains, before the sort of understanding of deep brains. In the old times, people were not so much interested in type 2 theories because they would not give rise to some interesting physics in 4 dimensions once you come down to 4 dimensions. Now, of course, the story is completely different with the presence of deep brains, with the fluxes, and so the whole situation is different. And I think Anna Maria will probably cover some of that in her lectures. So in the old times, like this was more interesting. When I say old times, I mean 80s, late 70s, early 80s, the whole of 80s. So this was an interesting part here. And also, I think Clifford, mentioned that SO32 is one of the gauge groups for which there are no anomalies. There is no gauge anomaly, there is no gauge gravitational anomaly. So this is anomaly-free theory. Okay. So this was the story. Somehow this anomaly freedom here, the anomaly free, by that I mean really going through a field theory, 10-dimensional super gravity theory, and look at the possible anomalies and try to find out that for this particular gauge group, the anomaly is cancelled. Right? But in string theory, the anomaly cancellation manifests in a very different way. And I don't know whether Clifford mentioned about that, but that basically comes from the tactile cancellation conditions. I don't know. Okay, but maybe that will become more clear when you talk about the deep brain exchange of the gravitons. Okay, so this was the thing what was known, say, in the late 70s and early 80s. Late 70s and early 80s. In fact, around 80, I don't know the exact date, but probably it was 84, when there was a famous paper of Green and Schwartz came. I think it was 84. Green, Schwartz paper came. Who actually showed that for SO32 there is no anomaly, but in fact they also found another solution. Okay, it was not just SO32. The anomaly cancellation implies 2 possible gauge groups, SO32 or E8 cross E8. There were 2 possible solutions of anomaly cancellation. On the other hand, string theory could only realize one of them, at least at that time. Until 84, the only string theory that we knew, which was anomaly-free, was the SO32, not the E8 cross E8. And in fact, E8 cross E8 could not be obtained within the framework of open string. Okay. This maybe again has been mentioned that in the type 1 theories, unoriented type 1 theories, the only possible gauge groups that can appear is either orthogonal groups or symplectic groups. Okay. And the anomaly, the tadpole cancellation finally picks out SO32. However, there was no possibility to get E8 cross E8 in the framework of open string. So this was a puzzle after the Green-Schwarz result, and that puzzle was solved like within a matter of few months. The anomaly cancellation paper of Green-Schwarz came, and then like 2 or 3 months after that, there was this famous paper of Gross et al. Gross, Harvey, Martinek, and Rome. Right? So this paper came out, which was probably again late '84, maybe December of '84 or January '85. And what they did was to actually obtain also a string theory description for the E8 cross E8 case. And again, it's n equal to 1. So how they obtained that? Well, the way they thought about it was, we had this closed string. Well, we already know that open string theory, unoriented open string theory cannot give E8 cross E8. Right? So then the next possibility is to go back to the closed string theory and see, can we do something in the closed string theory, okay, which would give rise to, first of all, n equal to 1. Instead of n equal to 2, you get n equal to 1. And then furthermore, get E8 cross E8. And this theory was called heterotic. So this was the last theory. I mean, this will complete the superstring theory that we know in N-dimension. So we have these 3, and then this heterotic string theory, which I'll be describing in the first lecture. This will be crucial because I need to discuss various dualities between these different string theories. So I need to first of all develop the ingredient. What is the heterotic string? So that will be the first one. So first lecture will be heterotic. Theory. In fact, we'll see that in heterotic theory you get both of them, both SO32 and E8 cross E8. So there are two heterotic theories. The second lecture, I will start talking about the S duality. Second and third lecture, actually. And fourth lecture, again, depending on how fast I can, how much I can cover in the first 3 lectures, I will try to give some more detailed evidence for this S duality. So some evidences, some non-trivial evidences. I mean, of course, in the second and third lecture, I will give more or less trivial evidences, which had to be true. Otherwise, of course, the whole thing is completely wrong, right? The duality would be completely wrong. So I will discuss some trivial checks for the duality lectures, and then we have some more non-trivial. As I said, this will depend on how much time. So this will be the outline. Okay, any question? Not much to ask. All right, so let me go back to the heterotic discussion. So as we said, we have n equal to 2. And this basically comes from n equal to 1 from left movers. And there is another n equal to 1 from right movers. This is the way n equal to 2 appears syntactically. Right? So Gross et al. Thought, okay, why don't we do the following? Let's just take the superstring, the fermionic string, only in one sector. And in other sectors, we take the bosonic string. Okay, it's very natural. I mean, retrospect, it looks like a very simple step, right? So what Gross et al. Did was to take the fermionic string from the left movers and bosonic string. Bosonic string that Bartle talked about in the last week, during the last week. So bosonic string on the right movers. First of all, let's see. So, is it possible? Does it make sense? I mean, is it possible to construct something like this? Well, first of all, let's look at this fermionic sector. In fermionic sector, we have the x mu's and psi mu's, the worldsheet fermionic partners of the x mu's, right? This is the basic variables in the fermionic string theory. And this psi mu notice this psi mu is a fermion of the 2-dimension, or the world sheet is a world sheet fermion, but it's a space-time Lorentz spectrum, right? You see this index mu. This index mu is the same as the x mu index. So mu goes from 0 up to 9, right? And that is just the vector index. Okay? So psi mu are vectors of the space-time, but spinors of the world sheet. Now, the world sheet is 1 plus 1 dimension. So the world sheet is 1 plus 1 dimensional, right? One time and one space dimension. And in this dimension, there is something very special happens, that the 2-dimensional, this 1 plus 1 dimensional fermions, you can simultaneously choose them to be Majorana and Y. Okay? This doesn't happen in general other dimensions, but in 1 plus 1 dimension, you can choose both this psi mu to be Majorana and Y. This is a very special thing that happens in 1 plus 1 dimension. Actually, another place it happens is 1 plus 9 dimension. In general, it happens in 1 time, and 8 and plus 1 space. Yeah. You can impose both Majorana and Y dimensions simultaneously. So in fact, the next one is n equal to 1, which is 1 time and 9 space dimensions, which is what the string theory lives in. Right? But this happens also in the world sheet. Now, if you look at it, I mean, just to try to explain a bit more in detail, in 2 dimension, I can choose so in 1 plus 1 dimension, I can choose the gamma matrix in the following way. I can choose gamma 0 equal to, say, I sigma 2, and gamma 1 equal to sigma 1, where these are the Pauli matrices. Okay? And clearly you can see that they satisfy the Clifford algebra. And furthermore, gamma 0, the time direction has a signature -1. So square of gamma 0 square should be equal to -1. And that's the reason for this I here. Okay? So sigma 2 square will be 1, right? But the I sigma 2 square will be -1, whereas this is +1. Okay. Now, if you write down, so in this basis is very convenient because the analog of gamma phi, which measures the chirality, is diagonal. So it is a convenient basis because the gamma phi, analog of gamma phi in 1 plus 1 dimension, is just the product of gamma 0 and gamma 1, which is proportional to sigma. Sigma 3 is diagonal. So what this tells me is that the 2-component spinor, the spinor of course is 2-component spinor because these are all 2 by 2 matrices. Gamma matrices are 2 by 2 matrices in 2 dimension. So it's 2-component. So the upper component and the lower component. So one component is, say, left-handed, not left movers, left-handed in the sense of chirality, left-handed, and the other one is right-handed. And furthermore, you can choose both of these components to be real. The reason is, you see that these gamma matrices are real. Sigma 1 is clearly real. This is 0, 1, 1, 0. Whereas this one is I times sigma 2, which is 0 minus I 0, which is again real. Right? So gamma matrix is real. So you can choose these components to be real, and then when you multiply the gamma matrices, it still stays real. Right? So you can impose reality condition. And of course, you can also choose, for example, your fermions to be purely left-handed or purely right-handed by imposing the condition of chirality. Right? You can impose the condition, the 1 plus sigma 3, plus or minus sigma 3, acting on psi equal to 0. Either plus or minus, depending on your choice. Right? So you can impose both the chirality condition, say that your fermion is only left-handed, as well as Majorana condition. Furthermore, this handedness of the fermions is actually also related to the movingness, left moving or right moving. It turns out left-handed is purely left moving and right-handed is purely right moving. And the way to see this is look at the Dirac operator. The Dirac operator acting on this side. So what is Dirac operator? This is simply gamma mu, d mu psi, but then you write it down. So gamma, this is gamma 0 dt plus gamma 1 d sigma acting on psi. and just choose this, just write down gamma 0, and sorry, gamma 0 and gamma 1, then you find that this is 0, d0, d0 plus d1 plus d sigma, I mean dt plus d sigma, and minus dt plus d sigma, 0, acting on, let me call it psi L and psi R. Psi L and psi. So this is a left-handed, so psi L means left-handed, and psi R means right-handed. And this is the Dirac operator acting on these guys, and the Dirac equation would be this is equal to 0. So you see immediately that the equation satisfied, the equations are dt plus d sigma acting on psi right is 0, and dt minus d sigma acting on psi left is 0. So the solution of this equation, the most general solution, is that psi left is only a function of t plus sigma, and psi right is only a function of t minus sigma. So that shows that the handedness and movingness are correlated. Right? Okay, so you see, because of this, such a statement makes sense. You see, if this was not true, the statement that Gross, I mean the conjecture that Gross et al. Were making, that let's just take the fermionic string on the one sector, the left moving sector, and the bosonic string on the right moving sector would not have made sense if this was not true. So the very, very basic requirement is met already the first step. So this is fine, you just choose your fermions are just psi and psi left mu, and they are all left movers. They are only functions of t plus. So therefore the content here, the content on the left moving sector, the field content of the left moving sector is x mu left and psi mu left.
So one question. Is this also true well, this is true in 1 plus 1, but it remains true in 1 plus 8 and plus 1 signature?
This the fact that you can impose both Majorana and Y, that is true also in.
But the correlation between handedness and movingness?
No. This movingness is only a concept of in the 1 plus 1 dimension. Okay. Because in 1 plus 1 dimension, I mean the space direction is only sigma. So either something is moving in positive sigma direction or negative sigma direction. Right? So then you can talk about a wave, a wave which is moving in the left, and a wave which is moving on the right. Right? More than higher dimension, this doesn't.
Oh, well, it's just because in other lectures we were thinking of this left and right movers using the first two coordinates of, say, 1 plus 9.
Sure. You can do that partially by going to some two-dimensional subspace. Yeah. Okay, that you can. But in the whole space, you can. Actually, this was very important, in fact. I mean, the fact that in 1 plus 9 dimension, that is a 10-dimensional space-time, that you can impose Majorana while simultaneously was actually very crucial, which you must have seen, I think, in Carmen's lectures. Right? Because, I mean, if you think about it, maybe I should, let me just say this. Okay, here let me just say this. If you look at the Navier-Stokes sector, let's look at the NS sector in the type 2 theory, NS sector in the left movers. Let's just look at focus on the left movers. So I have this NS sector. The NS sector is obtained by, so what is the NS sector? So the master states are obtained by applying alpha minus 1 acting on the Navier-Stokes ground state, right? And how many of them are there? Well, you can go to the light cone gauge. Again, I don't know whether Carmen did in the light cone gauge or covalent gauge. But in any case, if you want to study the physical mass spectrum, it is much more convenient to go to the light cone gauge, where you directly find the physical states. So let me go to the light cone gauge. So this index I is in the transverse direction. And how many of them are there? In 1 plus 9 dimension, the transverse directions are 8, right? So this is 8 dimensions. That right? Sorry? Sorry. The fermionic string, yes. It's the fermionic oscillators, psi I. I think usually we call it Bi minus 1. Yeah, they are. Sorry?
The frequency is 1 half.
Yeah. Bi minus half acting on the ground state. So these are 8 of them. Okay. Now if you look at the Raman sector, when you go to the Raman sector, you have the Raman ground state, which is the SO 1,9 spinner. Right? Is the SO 1,9 spinner. SO 1,9 spinner is 32 dimensional. If you write down the gamma matrices in 10 dimension, they are 32 by 32 gamma matrices. Okay? So these are 32 dimensional. Okay, these states are of course on shell, right? I mean, in the string theory, whatever physical states you construct are on shell, which means, for example, in the bosonic case, they satisfy p square equal to 0. In the fermionic case, they have to satisfy Dirac equation, the master's Dirac equation. So that will cut down from 32, cut down by half. So from 32, the on-shellness will only bring it down to 16 components. And moreover, you see, a priori to begin with, 32 component fermions are complex fermions, right? So when you go on shell, you'll get 16 complex. That simply doesn't make sense because here you have only 8 real degrees of freedom in the Lebesgue-Schwarz. Now, if you have space-time supersymmetry, the number of freedom in Lebesgue-Schwarz and Raman must be equal, right? So here again, you must have 8 real degrees of freedom. So how that comes about is that, first of all, you impose Majorana condition. So this 32 becomes real, so this 16 becomes real, right? And then you impose a while condition, and that cuts it by further half. So when you impose, so these are to begin with complex. So this is also complex. But when you impose Majorana plus while condition, it becomes 8 real. And that is why there's a space-time supersymmetry in the supersymmetry construction. By the way, this thing happens by the GSO projection precisely takes care of that. The GSO projection precisely imposes the while condition on the screen. So that's how the two things match. So it was crucial. Actually, this also, the fact that SO in 1 plus 9 dimension, you have Majorana while, has played a very crucial role in the construction of screen. Okay, let's go back here. So left moving sector is just x mu left and the corresponding fermionic partners. And as we saw, this makes sense. Now what about the bosonic string? The bosonic string, on the other hand, we know the critical dimension is 26. So here, I must have 26 x's, okay? Right moving x's. Now this, at first sight, it looks strange. I mean, how come here you have only 10? So these are 10. Whereas here you have 26. Well, the idea is to split that in terms of the x mu, right? And something else, xi r, where there are 16 of them. I mean, 26 minus 10 is 16. 1 after 16. You combine these two things together, and these are the standard x mu's that you have, right? The standard non-compact x mu's, which are the coordinates of the 10-dimensional Minkowski spacetime, and these are the psi mu left. And then here are some quantities which are purely right, some bosonic, scalar coordinates, which are purely purely right movers. So the question then is, what does it mean? Left movers, right movers mean these are functions of only t minus sigma. Whereas here, these are only functions of t plus sigma. So the main question now here is to try to make some sense of these quantities. X mu, the x mu, there is no problem because when you combine this x mu left and x mu right, that is the standard x mu that Clifford was talking about. In fact, he was splitting x into two components, right? Left moving and right moving. So that part is fine. So the main question is to understand, what these objects are. So that is the next step. So maybe it's difficult for people from here to see this, right? This blackboard, this part. Okay, I will keep writing here. Okay. So let's write down for x mu r, xi r. So those were the 16 directions, extra 16 directions, which are only right modes, right? So what will be its mode expansion? Well, there will be some zero mode xi plus some linear terms, but now notice that this is only a function of t minus sigma. So this object must also depend on t minus sigma, not just t, right? For the usual x mu, you just have p mu t, right? But now t must come with a sigma. And then you have the oscillator modes, alpha n, e to the I n, and t minus. Something like this. I'm not being very careful with alpha primes and so on. I mean, alpha prime you can put by dimensional analysis. So the important point here is that this depends on t minus c. But what that means is that this xi must be angular variable, right? Because after all, there is a closed string periodicity condition. You have the periodicity condition that x of any of sigma plus 2 pi should be equal to x of sigma. Right? This is a closed string periodicity condition. That's periodicity condition. This should be generally true for the closed string, right? That's how you define what the closed string is. But here, if you look at, whereas this part is fine, this part just requires that this n is integer, right? But this part is not. This part, it actually shifts xi. But that means that this pi must be quantized, right? Pi must be living in some lattice. Okay? For a single circle, it is just a statement that what, for example, Clifford was just talking about in the last lecture. You have x9 compactifier on a circle of radius r, then you identify x9 with x9 plus 2 pi r, right? You identify the 2 points. But now I have 16, these are 16 dimensional vectors, right? So we have 16 kind of angular variables. All these xi's are angular variables. That's what this says. So we are saying, we are saying that this xi are coordinates of a 16-dimensional torus. So circle to the power of 16. So 16-dimensional torus. So that's the first thing. To make sense of this xi's, I'm forced to think of this xi as not some non-compact variables, but as coordinates on some torus. Of course, if the coordinates are angular variable, then you also know the momentum, the coefficient of the t, should also be quantized. That should also be in some quantized things. Now, there is a convenient way of thinking about any d-dimensional torus. Okay? One convenient way of thinking about is to take Rd, I mean the d-dimensional real Euclidean space, and quotient it by some lattice, a d-dimensional lattice. So you are taking any points in this Rd, but identify 2 of the points which differ by one of these lattice vectors. So this is this guy is a d-dimensional lattice. That's a convenient way of thinking. So which means that some point x, say some vector x belonging to Rd, okay, is identified with x plus any, let's say this even maybe, okay, doesn't matter. Some lattice vector p, where p belongs to now. So you identify this way. So that way you get a 16-dimensional torus. The d-dimensional torus. So then what we conclude is that this coefficients, these p's, there are 16 of them, so you can think of it as a vector. These p's are nothing else but elements of this gamma 16. So these p's belong to gamma 16. So this is what so once you think about this compactification in this way, at least there is no obvious contradiction, right? Everything seems to work, and then we can start quantizing this string and start trying to find out what is the master spectrum, right? What is the spectrum in general, right? And in particular, focus on the master spectrum. But fortunately, all those ingredients you already have learned from the last week, right? So I just have to put them together for this hydraulic string, and then we can. So now let's look at the spectrum. So for the spectrum, the main important point is to remember is what is the L0 and what is the L0 tilde. So this is a left-moving Virasoro, and the zero mode of the Virasoro generator. We have seen this language, right, last week? So L0 is, again, I'm not going to, okay, let's say some number times alpha prime times p mu square, we'll say that's m square, mass square. So let's write down, so what is, plus the number operator n, okay? This, again, I hope you remember this language. This number operator is, again, if you wrote it down, which is basically alpha, say I go to the right phone, minus n, alpha, n, some n, positive. Plus the fermionic terms, Again, fermionic oscillators. So that just counts what's the total number of oscillators that you have put in. And then there is this intercept, which is different for the two sectors, Lewis-Schwarz and Ramon, because remember, left movers is a fermionic string, so it has two sectors, Lewis-Schwarz and Ramon sectors. So for the Lewis-Schwarz, it is half for the NS and 0 for the Ramon sector. So this is the standard thing that you have seen last. What about the right movers? So here you have again alpha prime p mu square, which is again p. So what are the momentum here? You see, besides this, I have also x mu to the right movers, right? X mu of the standard. So that will just give me p mu times t, and that p mu square will enter also in the right moving Virasoro, which is this, which is again the mass square. But now we have additional momentum, this 16-dimensional momentum. Okay? So we will also have a term like p vector square. So this vector is 16-dimensional. So this p belongs to gamma 16. That is simply coming because when you write out the Virasoro generator, the right moving Virasoro, it is d minus, that means dt by minus d sigma of xi whole square, right? So when you take dt minus d by dt minus d by d sigma, you get some 1 or factor of 2 or something like that from here. And then you have to take the square, so you'll get a pi square, right? That's exactly the pi square term. And again, I will choose my normalization, meaning that I will already absorb alpha primes and so on and so forth, so that this is dimensionless, and I will also normalize it in a way that it's 1/2. Just for convenience, it's not big. You can keep alpha prime if you wish, but it's not. It's more convenient. So I have normalized it in such a way that it's 1/2 p square. Plus, we have n tilde. N tilde is just the right moving oscillators. Again, here just replaced by alpha tildes. So let me write it down. I think it will be n greater than 0 of alpha I tilde. Tildes are the right moving oscillators. But we also have the other ones. Alpha I tilde minus n, alpha tilde. So this is, I mean, there is no fermionic term here. This is purely bosonic string. The right moving string is bosonic. So, that entry is this here. So these are the usual transverse coordinates in 10 dimension. So I goes from 1 up to 9, 1 up to 8. So this I goes from 1 up to 8. And this capital I goes from 1 to 16. So this is the thing. I mean, total is 24. the bosonic string, 24 transverse directions. Okay. And then there is of course a -1. This for the bosonic string, there's an intercept is -1, right? This is the normal ordering ambiguity, which is fixed by requiring Lorentz invariance. Right? This you have seen, right? All right. So with this now we can write out the entire spectrum. And let's focus on the massless states. Let's focus on the massless states because that's the most crucial. To have massless states, from the left moving sector we already know this is standard fermionic string, right? Fermionic string. So the left movers is a standard. You have in the Navier-Schwarz sector, you will have, because the intercept is half in the Navier-Schwarz sector, the massless states are obtained. Maybe I should just write down the fermionic part. The fermionic part of the oscillators. Fermionic part was in the Navier-Schwarz sector is B n minus n minus half B n plus half. Because in the Navier-Schwarz sector, the fermions are antiperiodic as you go along the sigma direction. So the Fourier modes are half integer modes, right? So that's why you have it. There's a shift by half times n plus half. This is the VI, again the transfer directions, and n goes from 0 to infinity. That is the for the Navier-Schwarz sector, and in the Ramond sector, it's simply there is no intercept, and it's just VI minus n. That's the fermionic. So that's the standard. So for the left movers in the Navier-Schwarz sector, the massless states are VI minus half acting on the Navier-Schwarz ground state, and there are these are just 8 of them. And in the Ramond sector, these are simply the Ramond ground state. So these are this you remember how it works out, because in the Ramond sector there is also D0. N can also be equal to 0, right? So you have a D0, and D0 satisfies the Clifford algebra, right? And therefore, the vacuum of the Ramond state will be a spinor of the Clifford algebra, I mean spinor representation. And then once you do the GSO projection, etc., you find, for the reasons I mentioned there before, that this is again there are eight real states. Once you impose the Majorana condition and the GSO projection, then you find. So that's a complete matching there. Now what about the right movers? Because this is the new thing now. So in the right movers, you have this, this is equal to 1, intercept is 1. So to have m square equal to 0, because remember, on the physical state, L0 tilde and L0 should be equal to 0, right? So on the physical state, this quantity must be equal to 0. So in particular, we are looking at the massless state, so m square equal to 0. So that means that this must be equal to 0. Right? So there are two possibilities. So one possibility is n tilde equal to 1 and p equal to 0. This is one possibility. Right? Because p square, if p equal to 0, p square is 0, and n tilde equal to 1, so that becomes 0. How many states are there? These states, I can write it as alpha tilde minus I minus 1 acting on the ground state, or alpha tilde capital I minus 1 acting on the ground state. Altogether 24 states. There are 8 here and 16 there. That's what you have seen in the bosonic string. You have 24 transverse states, right? I just separated them because you see, I want to see, because our Lorentz group is really SO1,9, right? So this will be vectors under SO1,9, or more precisely the transverse subgroup of SO1,9, which is SO8. But these will be scalars, right? The SO1,9 doesn't do anything to that, right? So this is the reason why I have split them in 2 categories. But altogether there are 24. But now the more interesting states are the second type, where I choose n tilde equal to 0 and p vector is non-zero, in such a way that p square equal to 2. So suppose in your lattice, I mean, of course, now whether such a state exists or not depends on the lattice, right? Because remember, P is a vector of the lattice. So it could be that there is a lattice where there is no such vector, whose length square is equal to 2. In my normalization, I have the way I have normalized it, right? In that normalization, maybe there is no vector which is P square equal to 2. In this case, there will be no such massless state. Okay? But suppose there are some such states. Your lattice is such that there are some states, then again, you find a massless state, right? And this massless state, since n tilde equal to 0, you have just a ground state as far as the Fock space is concerned. There's no creation operator applied here. Right? There's no oscillator state applied, operator applied there. It is just the state E. Okay? So the total number of states that you will find which are massless, it clearly depends. I mean, there are 24 from here. Of course, there are 8 here, that is fine. So if I focus on Lebesgue sector, I have 8 times 24. Right? But then you can also have 8 times some number of states here, and this number of states depends on your details of the lattice, what kind of a lattice you have. So this depends on the lattice. This depends on the type of lattice that you choose, gamma 16. So next question immediately arises, is there any condition on this lattice? I mean, could I have chosen any lattice, or there are some stringy conditions, right? On the lattice. So is there some consistency requirement for the string theory that you should only choose some particular type of lattices? Okay? So that is the next question. And but anyway, let me just stop here. But let me before going there, before going to this, let me just mention one. So what are these states? I mean, the physical states you have to combine the left and right movers. So let me just combine now. And let's just focus on the Lebesgue sector, because if I know the content in Lebesgue sector, in the Raman sector, it will be just super partners. Because once you have done DSO projection, we have an n equal to 1 supersymmetry, which relates the Lebesgue to Raman, exchanges Lebesgue to Raman. So we are guaranteed there is an n equal to 1 supersymmetry. So if I know the bosonic spectrum, then the fermionic spectrum will be just the super partners. Okay. So I don't have to talk about it. So let's look at the bosonic states. So this will be Bi minus half times alpha tilde. So this is the right vacuum, Lebesgue vacuum, minus vacuum, and then here is minus one, say J, 0, right movers. So I'm taking the product of this with that. That's one type, and then I have Bi minus half 0, minus, and alpha tilde I minus 1, 0. And then finally, I have, if such states exist, then I have also so these are the states, massless states. And now let's look at what kind of states these are. This is a vector of the SO1 from 19, or SO8, the transverse group SO8. This is also a vector of SO8. So this is the second prime tensor of SO8. And as usual, you can decompose in terms of the traceless symmetric part, the trace part, and antisymmetric part. And that just gives you the standard G mu nu, D mu nu, and the delta. So the content of this, once you go back to the covariant language, I mean, here is a light cone. And once you go back to the covariant language, this will become the metric, antisymmetric tensor, and the delta. So this is pretty universal. Basically, in all string theories, you have this. Except in type 1, this is projected out, but this reappears in the Raman sector. So it's pretty universal. These are new. Let's look at these states. This is a vector. This is a scalar of SO8. So these are gauge fields. You see, this is a vector. So what you find is you get gauge fields, but with the index I. Right? For each I, there is one gauge field. So we see that there are 16 gauge fields here. And these are actually U1 to the 16 gauge fields. because these are different xi's. These are different xi's, and these two different xi's do not have any non-zero correlation functions between them. They don't talk to each other. Okay? So these are for each I, you get one U1 gauge field. So there are 16 U1 gauge fields there. Now, what about these states? So these states, okay, if they exist, then there will be some states. If there are such lattice vectors exist, then again we'll find vectors, because this is again a vector. AP mu, I label it like that, AP mu. So these are again gauge fields. But these gauge fields, you see, they are carrying momenta. This P has momenta along the different capital I directions, right? So they will interact non-trivially with this A mu I, which means, in fact, this P are nothing else but the charge with respect to this. The ith component of this P is nothing else but the charge with respect to this gauge field. In other words, this U1 to the 16 is a Cartan, because there is a abelian subalgebra. So this is a Cartan subalgebra. And if such P exists, they promote this abelian subalgebra to a non-abelian algebra by giving the root vectors. These P's are nothing else but the root vectors. So P's, viewed from this point of view, P is such that, I mean, they satisfy this P square equal to 2 condition, they are root vectors. Okay. Yeah, they are root vectors. In some sense, I mean, yeah. I mean, one can see it from, again, from, I mean, this the statement that this P are the roots with respect to this Cartan. One can understand it from the discussion that Clifford made. You see, I mean, if you look at this, these states here. This, I mean, okay, think of, I mean, at the moment, of course, this is space-time that's internal. Okay? But just imagine, it's not true, but just imagine that all of this is part of the big space-time, and I just compactified this direction. Then the symmetric part of this will be like the metric, the G, right? And the antisymmetric combination of this will be antisymmetric B field, the Navier-Stokes field, right? And what Clifford showed was that the Kaluza-Klein momentum is a charge with respect to the metric, and the winding mode is the charge with respect to the B field, okay? The antisymmetric part. And when you write something like this, carrying the momentum here, so this has, you see, both the parts. It has a momentum part as well as a winding part. Okay? So these are the charges with respect to, say, the symmetric and antisymmetric parts. Okay? I mean, it's roughly, you can see this, but more precisely, you can just directly compute the amplitude and just compute 3-point function and get the structure constants. One can do that. But at the end of the day, after doing this calculation, you find that these are nothing else but the root vectors, where this is now the Cartan. I mean, this U1 to the 16 is the Cartan subalgebra. And this P are the root vectors. So if you have a lattice where there is no such vector, P square equal to 2, you just have the gauge group U1 to the 16. And more generally, if you have some vectors like that, they will be just the root vectors of the corresponding non-abelian. So now it becomes very crucial to find, is there any restriction coming from the consistency of the string theory on the gamma 16? Because the nature of the kind of gamma 16 will tell you what gauge group you get, you know, in 10-dimensional theory. So that is the important one. Now we know from the anomaly cancellation conditions, we have an SO32 or E8 cross E8, right? So question is, so there are two questions. Can we get E8 cross E8 or SO32 in this framework? And secondly, why only this? Why not something else, right? So that brings, I think this, I'm not sure if this has been discussed in the last week. Have you seen partition functions? You have seen partition, for both for bosonic and fermionic string? Bosonic string you have seen. Okay, so let me just, okay, I think I will not need too much details, but nevertheless, something. Did she talk about modular invariance? Mm-hmm. She talked about it? Oh, very good. So let's look at the one loop string partition function or string amplitude. It doesn't matter. But let's look at the string partition function. Sorry, the question. So what is the one loop diagram? One loop diagram, one loop worldsheet diagram is just that. So partition vacuum diagram, no insertions. If you have insertions, as you just insert some operators to compute some amplitude. But let's first look at the vacuum amplitude, no insertions. So it's just a path integral over this worldsheet torus. That's the one loop diagram. Now, so this is just the worldsheet is a torus. Worldsheet is a torus, two-dimensional torus. But as we said, from a general discussion, T2 can be thought of as R2 divided by a two-dimensional lattice, right? Think of it that way. Which is, in the two-dimensional case, you can draw a picture. I have R2, and you just identify, say, this point with that point, this point with that point. So then you get a parallelogram. So lattice. So this is a picture where I've chosen basis vectors of the lattice like this, E1 and E2 as the basis of the lattice. Then lattice would be gamma 2 will be the set of all n1 E1 plus n2 E2. This will define to me for n1 and n2 integers. This defines to me a lattice, right? And you identify 2 points which differ by any such vector. So you see that you can bring, if you look at this one basic cell, one parallelogram, okay, then any other vector, which is any other point is outside, can be brought about by such shifts to inside the parallelogram, right? So therefore, you can just remove all of that and just take one copy of this because everything else is identified with that, right? And furthermore, this edge is identified with that edge from this shift. So this becomes a cylinder, right? Because you identify these two. And similarly, these two are identified. So this cylinder is again closed, and you get a torus. So it's very easy to visualize the two dimensions. So you choose this lattice, so some lattice. And now, of course, in the worldsheet, well, for a general torus, it will be that, right? So, but in the world, of course, you can by choosing, there is, of course, a rotation group here. I can always bring one of the basis vector along the, say, one particular direction, right? By choosing it. There's a huge amount of freedom in choice of this. I can rotate this whole thing, doesn't change anything. If you just rotate both the E1 and E2, doesn't change anything. No physics is changed, that is. So I can always bring one of them along one direction. But here we have more than that. So if you do that, how many parameters are there? So I brought this into along, say, x-axis, and here is the y-axis. I brought this along this direction. So its length is one variable, and here you have the length and the angle, right? So you have three variables. So three real variables are defining a torus. A two-dimensional torus is defined by giving three real variables. However, here we have a little more than that. It's not just a rotation. We have also scale invariance, right? Because after all, we are talking about a conformal invariant theory. You can scale, right? So by scaling, for example, I can bring this length equal to 1, right? Some standard, whatever your choice is. So that is no longer a parameter, right? So in a theory, the string theory, the actual number of parameters is only 2, not 3. Because by scaling, you can get rid of one parameter. So you have only 2 parameters left over. So a convenient way of thinking about it is make this length equal to 1. So this is 1. And since it's a two real dimensional space, I can equally well think of as one complex dimensional space, where this is the real part and that's the imaginary part. I can think of it like that. Then the second vector is simply given by one complex number, right? Tau, let's call it tau. So tau has so this part is the real part of tau, and this part is the imaginary part of tau, right? So one complex number defines to you a torus, conformally inequivalent torus, because I've already used a scaling property. So different taus give you conformally inequivalent tora, and that you have to integrate over in your string theory, right? Because again, you see in the Polyakov picture, Polyakov description, this is just a side remark. you have not only the path integral over all the x mu's and all the psi mu's and whatever your fields are, or in this case there's also dxi and so on. All of this integration is there, but also I have the integration over the metric, g, little g. Little g was the worldsheet metric. Remember in Polyakov description, you introduce a intrinsic worldsheet metric GAB, right? Remember the Polyakov action was B2 sigma root g minus g. Let's say we have a Euclidean, so plus g, Euclidean signature, GAB, dx mu, dx mu, the flat space line, eta mu, plus, etc., etc. So there is this metric GAB, which you introduce to define the Polyakov action. But GAB is not a really physical object, right? I mean, it's something you define, you introduce to define your action. You would have written Nambu-Goto, right? Nambu-Goto does not have this intrinsic metric. But it doesn't matter because GAB is a symmetric 2 by 2 matrix. It has 3 functions inside, right? The 2 by 2 symmetric matrix has 3 components. So there are three functions involved in the GAB, right? I mean, the GAB is, okay, there's something here, something here, but it's symmetric. These are all functions of, let's say, G11, which is a function of sigma t, and so on, everything else. But they're symmetric, so there are three functions inside. Right? But you have 2 diffeomorphisms in the worldsheet. So 2 local diffeomorphisms. So 2 of these functions you can get rid of by using diffeomorphism. That leaves 1 function, but then you also have the wide invariance, scaling, local scaling, right? Which is another function. So you get rid of all these 3 functions. However, so even though you have gotten rid of these 3 functions, so which means a function is infinite dimensional, right? A function is infinite dimensional because it's a function of some variable. So you have removed 3 infinity worth of objects by using diffeomorphism and wide. But sometimes it can happen, there is some finite number of freedom is still left over. Right? So those finite, so by using this, so you have this integral over this metric also in Polyakov formulation. By you fixing the diffeomorphism and while, you can get rid of almost all of these integrations, except perhaps a finite dimension. Not a functional integral, but some finite dimension. And that finite dimension, how many dimensions are finally you get depends on which genus of the Riemann surface you're talking about. For the torus, it is just 1 complex dimension, and that is exactly this tau. Indeed, you can see that this tau is, so what is the dimension left over? Once I fix the parameterization, and once I fix the Y scaling, what is left over is what you have to integrate over. And we already argued that tau is left over, right? Tau is parameterizing conformally inequivalent tori. So I have to integrate over tau. So in this path integral, for the case of torus, this essentially, I mean, I'm simplifying, there's a lot of stuff goes into it. Because when you fix the gauge, you have to introduce Fadi-Poco. So there's a whole machinery there. But the main point I want to say is that, okay, from this dg, from this integral dg, what is left over is simply d2 tau. That's what's left over. But okay, there are a lot of technical issues inside there, but this is how I'm trying to focus. But on the other hand, we said different taus parameterize inequivalent tori. This is not entirely true. That's a local statement. I mean, if I start with a tau and change tau a little bit, that's going to give me another tori. So for example, if I start with this tau and change the tau a little bit, so from here to here, so I'll get another torus, which is conformally inequivalent compared to that. But what if I do some finite transformations, some particular finite transformations? For example, let's take a transformation where tau goes to tau plus 1. That means I've got a new parallelogram, which is this. But this parallelogram is nothing different. I mean, it was already, you see, tau plus 1 was already an element of the lattice. Right? It is just that you have chosen a different basis in the same lattice. Right? So that is not a different torus. So not all taus are conformally inequal. Different taus may be describing the same torus. But that is simply a question of how many independent bases you can choose here. Okay? Now, you know that if it was not a lattice, if it was say R2, and you choose a basis, and another basis will be related by an SL2R transformation, old basis. But now we are not talking about the R2, but we're talking about the lattice, right? So the SL2, so the two transformations which are relating two different choices of the basis for the same lattice are SL2Z, where the elements of, I mean, what I'm saying is,
because the coefficients can only be
exactly, coefficient, yeah, because it has to map a lattice vector to another lattice vector. So the coefficients in SL2 must be integers, right? So what we are saying here is that any two, so if I choose some basis E1 and E2, let's say E1 and E2, then I can change the basis to E1 prime and E2 prime, which is related by an SL2Z transformation A, B, C, D of E1, E2, where A, B, C, D, this belongs to SL2Z. Z just means that all these coefficients A, B, C, D are integers, and SL2 means determinant is equal to 1. So this means A, B, C, D are integers, and AD minus BC equal to 1. So this is the thing which is left over, right? We haven't fixed that. So we shouldn't overcome. I mean, when I integrate over tau, I shouldn't be integrating over all taus. I should be integrating only those taus which are, so integrate over taus modulo SL2Z, right? I mean, I should overcount. So that is what is called the fundamental domain. But anyway, that's another issue. So main point here is this, okay? So we have this SL2Z invariance. It should be, this is what's called the modular group. This is a modular group. For one loop. For higher loops, it becomes more and more complicated. But say the one loop is a modular group. And your theory must be invariant under modular transformations for consistency. Otherwise, the system theory is inconsistent. So this is the main point. Now, you can ask the question how this acts on tau. So you can easily verify. You see what happened. What did we do? I mean, here what we had some E1, E2. We rotated the E1 to along the x-axis, and we put E2 in the upper half plane without losing any generality, right? I can do that, right? Because even if I had lattice like this, I could choose the lattice such that the E2 tau is in the upper half plane. So I can always restrict im tau to be positive, imaginary part of tau to be positive without losing any generality. So now you can ask, after I do the rotation, SL2Z transformation, I get a new basis. I can do the again. E1 prime, I can take it to x-axis, real part, and E2 prime I can take on the imaginary, positive imaginary part. And you can convince yourself that under this transformation, tau goes to tau prime, where tau prime is A tau plus B divided by C tau plus D. Maybe this A, B, C, D are not the same as those A, B, C, Ds, but there are some permutations of these A, B, C, Ds. But I mean, it is something like this. I mean, here again, AD minus BC, this is satisfying, AD minus BC. So this is how tau transforms. And what we are saying is that the theory should be invariant under such a transformation. It's actually a little bit difficult to handle with this. There are too many transformations here. But it turns out that this entire SL2Z is generated by these two elements, by tau going to tau plus 1, which sometimes people call it T transformation, and S transformation is this tau going to minus 1. You can clearly see. I mean, if for example, this corresponds to choosing A equal to B equal to 1 and C, A equal to B equal to C equal to 1 and D equal to 0 here. And this corresponds to A equal to 0 equal to D and B equal to minus C equal to 1. This would be. When I say generated, I mean not in the sense of Lie algebra. No. These are all finite group elements. I mean, not in infinitesimal. So when I say generated, I mean any element like that can be obtained by successive applications of T and S. You see, they don't commute. These two actions do not commute. And so any element, what it means any element can be written as T to some power, S to some power, T to some power, S to some power, and so on. So the sequence of this. Any element can be written like this. Okay, that's what I mean by generator. So what this means is that if I can make sure that my theory is invariant under these two transformations, then I'm guaranteed that it is invariant under the full SL2Z. Because any element can be written as this, but since individual element like that leaves the theory invariant, so the whole SL2Z leaves it. So main thing we need to check is that our theory has this invariance under these two transformations. Okay, so how can we now? So we want to apply this now for the hydraulics. So now the actual path integral is very different. I mean, it's a long process. But fortunately for one loop, we can do it in a different way. It is much more straightforward. Yeah, so let me do it in this way. So let me draw this picture like this. So I think of this as the sigma direction, and that is the time direction. And my torus, this torus is this one. Okay, here I've normalized it to 1, although perhaps it's more natural to normalize it as 2 pi, because usually for a string you have length 2 pi. But anyway, that doesn't matter. I think Polchinski's book is probably always normalized as 2 pi. So here is tau. Now, if you think about this again, so to go from here to here, I can do it in 2 steps. I can first go along the time direction, or vice versa, doesn't matter. So this distance I have to travel is im tau. And then I go along this direction, the real power. Now, so what I want to do, so one loop diagram means I take a string, propagate there, and identify these two, right? What does it mean identify? It means taking a trace. I mean, if you think of it, so some wave function. I've created a wave function here, and then I get this wave function and identify this wave function and sum over order. So it's a trace. Okay? So I want to take the trace of the trace over all complete Hilbert space of what? But going from here to here, what I have to do? I have to evolve along the time direction by an amount im tau. So I have an operator e to the power of minus im tau, minus because I have again gone to the Euclidean, Wick rotated theory, times the Hamiltonian. Right? Because Hamiltonian is a generator of time translation. I mean the 2-dimensional Hamiltonian, world sheet Hamiltonian, im tau. And then also I need, that's not enough because I need to also go along the sigma direction. So I times real tau times the generator of sigma translation, but that is the momentum operator, right? Let me call it P sigma. This is the world sheet momentum, not to be confused with the space-time momentum. It's a world sheet momentum. So I have to take this operator and take the trace over the entire Hilbert space, over whatever the Hilbert space is of your theory. Right? And this is what you will do. I mean, in the ordinary particle theory, we don't have the sigma direction. You just one loop can be written in this. This is Schwinger language, Schwinger parameterization of the one loop diagram, right? So you can write it as you start from a particular time, you go up to some final time, and then you take the trace over the Hilbert space. Okay? And then I have to integrate over this time. This is the Schwinger time. Okay? So I have to integrate over dt over t, d im tau. Im tau is like the time over im tau. This is what would have happened already for the point particle, but now I have to also integrate over the real tau. So this becomes d2 tau. So that is the generalization of the point particle to string. For the string, you would have just d im tau. I mean, there will be no real tau there. There will be only im tau, d im tau or im tau, and then trace over the particle Hilbert space, and you have this thing. Right. I mean, purely from the string point of view, one can understand this in a geometric way. But I don't want to. I mean, it's simply because you haven't fixed all the, by going to this conformal gauge and all this, you have not fixed the entire gauge, because this torus has a translational symmetry, rigid translational symmetry. That has not been fixed by going to this coordinate system. So not all diffeomorphism has been fixed here. The rigid translation is not fixed. But the rigid translation, because it's compact, rigid translation, the volume of the rigid translation group is simply the volume of the torus, which is im tau. So I have to divide by that volume. So this has the nice meaning actually from the string, from the polar coordinate. But anyway, so we want this, right? Now what is H? Remember, L0 was the generator of the sigma plus translation. It took sigma plus to sigma plus infinitesimal transformation. Say epsilon plus. Epsilon minus times L0 tilde takes sigma minus to sigma minus plus epsilon minus. Right? These are this you have seen, right? The L0 and L0 tilde are just the generators of rigid translations of sigma plus, the right cone coordinates, sigma plus and worldsheet right cone coordinates, sigma plus and sigma minus. And H is a translation of T, and P sigma is that. So it's easy to see that H is basically is a combination of L0 plus L0 tilde. And I think you have to normalize by 2 pi because I have chosen the length equal to 1. So it should be like 2 pi. 2 pi L0 plus L0 tilde. Whereas P sigma will be 2 pi times L0. So sigma plus and sigma minus are T plus sigma and T minus sigma. So obviously, right, it's just a combination of these two. So then we have a nice expression of the, and the point is that we know L0 and L0 tilde entirely. We have the complete spectrum there, right? So I just have to substitute those, and I can get the function.
I'm sorry?
Yeah.
In assume of L0 plus L0, I think that you have to put the same fraction, right? Because H is equal to L0 plus C.
Not the C. Not C. The intercept, you mean the intercept. Yeah, that will be there. I already included the intercept in L0. You know, the formula I wrote, I just erased the formula here. The formula would be this here. L0 would be whatever this E square, U square, plus n minus half for the Navier-Schwarz and the 1, 0. So these things have to be there. These have to be, these are included there. In some of the literature, you will find L0 is only this part without the intercept, the way they define in some of the books. In that case, you have to explicitly put a minus half there. But I'll just put everything together. And similarly, L0 tilde was what I had written down there. So L0 tilde would be, I just write U square plus half E square plus N tilde minus. Yeah, so this I can rewrite it as some measure P2 tau over im tau, and then trace over whatever Hilbert space you have, the big Hilbert space you have, and it just becomes q to the power of L0, q bar to the L0 tilde, where q is e to the 2 pi I tau, and q bar is complex conjugate. That is just, I mean, you combine real tau and imaginary tau, and the way the combinations appears for L0 and L0 tilde will be opposite. So you'll get, in one case you'll get L0, you'll get L0 tilde. And this 2 pi is coming from this combination. Okay. So this is what you do. Now, we are only interested, I mean, we are really interested in the lattice structure, right? That's what we are, we want to ask the question, what this modular invariance, does it impose some condition on this? Because after all, P belongs to the lattice. So we are interested, our question is basically focused on, it's a very limited question, right? We just want to find out if there is any condition on gamma system. We don't want the whole gory detail, right? Because the gory detail had to be worked out already for the type 2 string, which I don't know whether Carmen didn't do it, right? You say Carmen didn't do it because there was no time, I think. But I mean, you can show that for the type 2 string, for the type 2 string where it's not this, L0 tilde is also a fermionic string, for the fermionic string. This is in fact modular invariant, that's shown. So what we want is really the additional piece. I mean, what is the lattice dependence on this? And that's much easier to study. And so let's isolate that. The lattice part enters only in L0 tilde, which is that. So here you get q bar to the remaining pieces, well, whatever alpha prime p mu square plus n tilde minus 1. But the lattice part is all contained here, q bar to the power of half p squared. And here I have a sum because I have to take the trace, and trace includes in particular summing over all lattice points, right? So I have a lattice, or the p belongs to the lattice. Now here, all these remaining pieces, I mean L0 and these pieces, you have to sum over all the oscillator modes, which means the Fock space, you have to sum over all the Fock space. And that is what, okay, that has a very interesting story by itself, but I don't want to go into that. That's also very interesting, but let me not go into that. Let me just focus on this part. Okay. Now let's look at the two transformations. So the first transformation, the two generators of SL2Z, the P transformation. By the way, this P and S should not be confused with the T duality and S duality. Unfortunately, it's the same notation. Tau going to tau plus 1, and this is tau going to minus 1. Now, when I take, let's look at first, this is the easiest to study. When tau goes to tau plus 1, and again, as I said, let's focus on this part. We're just focusing on this part. So, q to the half, q bar to the half p square. I mean, q bar goes to what? Q bar in this goes to e to the power of minus 2 pi I times q bar, right? Because remember, q bar is that. If tau goes to tau plus 1, obviously tau bar goes to tau bar plus 1. So you get an extra phase factor, e to the minus 2 pi I. But the point is that this is, I mean, if it was just q bar, there's no problem. This is 1, right? But this is, there's a raised to power half p squared. So you get here q bar to the half p squared. And here also you get half p squared. So if you want, if a theory is to be invariant under this transformation, you already get an immediate condition that the p squared must be even. There's already the immediate condition from this. So this means that p squared must be an even number, even integer, for all p belonging to gamma system. It's a very strong condition. The second condition, this is a little bit more complicated, but I will just sketch the proof because I think it's good to know this. Because I mean, this technique appears many places, and also if I just state the result, it will look very mysterious. I mean, why that result comes. So at least if I give some steps to the proof, it will probably become not so mysterious. The point here is that you see, I mean. So this is a bit complicated because look at this object. What is this object? This is e to the power of minus 2 minus I times 2 pi times tau bar times p squared. And I have a sum of it. Right? I just wrote explicitly q bar. Q bar is there. Now when tau goes to 1 over tau, obviously tau bar goes to minus 1 over tau bar also. So this has to be inverted. That's a bit complicated. It looks complicated, but it's not so complicated because after all, if you think, suppose it was not a sum, but it was an integral, right? And say this was some continuous variable integral. Then it's just a Gaussian integration. And if I put some source term, there, then source term you will get the inverse of this second order operator, right? So in the source term you will get 1 over tau bar. So that's the trick one. I mean, this is not a continuous integration. This is a discrete sum over lattice, but that technique will still. So the idea of using that technique is the following. So this is what this is the function we want, but let's try to consider a more general function. Let's call it this here, y, where this is defined by just shifting the momentum p by some vector y, of course same dimensionality, 16 dimensional square. So consider this function. So yeah. So this half here, so it makes it. Okay. So consider this more general function. So of course we are interested in f of 0. That's what we want to compute, but let's consider it more general. The reason why we consider this more general function is that this function is periodic in y. Because if I take y and shift y by some lattice vector, say p prime, where p prime belongs to gamma 16, then this sum doesn't change. Because if you shift, you'll get p plus p prime, and that is just the redefinition, call this some p double prime. And since you're summing over all lattice, it doesn't matter, right? So this function is periodic under such a lattice shifts. So that means I can do a Fourier series analysis, right? Therefore, this function, I can always rewrite it as e to the power of I, let's say 2 pi I, some k dot y times some coefficients f of k. Okay. These are the Fourier coefficients, where k belongs to the dual lattice, gamma star. So gamma star is a dual lattice. It's a dual lattice. The definition of that is simply the following. So gamma star is equal to all the vectors k such that, 16 dimensional, such that k dotted with any vector p of the original lattice is integer. For all p belongs to gamma 16. That's a dual lattice. It's clear, right? Because, I mean, by this definition, it's clear that if I look at this, if I take y to be y plus p for some p prime, then since k dot p prime by this definition is an integer, nothing changes. So that's exactly the generalization of the Fourier series. So the important point is that in this way of doing it, okay, this k is necessarily in the dual lattice. This k is necessarily in the dual lattice. So somehow we'll see at the end of this steps, the 2 or 3 steps, the original lattice sum will be transformed into a dual lattice. This is what we have. So let us just see this quick. I'm already over time. 5 more. Okay, I think I just finished that. At least the main steps. Okay, so the next step would be to compute this f of k. Well, how do we compute the f of k? Just the inverse Fourier series, the standard technique, right? So we just take this f of y, multiplied by e to the minus 2 pi I k dot y, integrate over all the 16 dimensionals, 16 y's, but y in what? Y should be in the basic cell of this lattice, right? Because if I shift y by lattice vector, it's the same value. You'll get infinity. You have to, where y is in the basic cell, of gamma 16. Like what we did, parallelogram. This parallelogram was a basic cell for the gamma 2. In this case, it will be some 16-dimensional hyper parallelogram, I mean hyper whatever. Okay, this basic cell to get integral over. Okay, this is what will give me f of k. And probably you have to divide by some up to proportional. Let me just put here proportional. But I think I have to divide by the volume of the basic cell. 1 divided by the volume of the basic cell. Anyway, that's a number. So we have to compute this here. Well, let's plug it back here. Then now you see that it's a Gaussian integral in y, right? You plug f5 back here. This is a Gaussian integral in the y, and then that will happen. What we were saying before. So if I just plug that back here, so we are integrating d16y in a basic cell, of e to the power of minus I tau bar, e plus I squared, times e to the power of minus 2 pi I k dot y. Now let's just change, let's call this as some y prime. Then let's call this as some y prime. And this becomes y prime minus p. But it doesn't matter because k dot p is integer, right, by definition, of the dual lattice. So this drops out, and you just get the basic, this is Gaussian integral. But what has happened is that, you see, y prime is y plus p. Oh, I forgot, there's also a summation of p. Y plus p. Now, y was the original basic set. But when I shift by all possible lattice vectors, that is the same as extending the integration range in the entire 16-dimensional Euclidean plane, Euclidean space. Just like here, if I shift this by all possible lattice vectors, then I will span the entire R2, right? So this integral simply becomes V16y over the full R16, and the lattice sum is gone. I've already done the lattice sum. And now it's a very simple Gaussian integral. And the result is, I mean, there's again this 1 over volume factor, whatever, and the result is, okay, up to some number again, e to the, I'm not sure. Okay, then you'll just find this, minus I pi minus 1 over tau bar, k square, some limit k square. I mean, this is f of k. 1 over volume factor, maybe there's some other, so let me just put here proportion. F of k is something like this. Proportional meaning is independent. This proportionality constant does not depend on k. The k depends entirely there. Now, if you compare with the original expression, right? So original f of 0 was that, right? E to the minus I pi tau bar p square. And remember, I erased that. This was equal to f of k e to the we did that, right? 2 pi I y dot k. We did the Fourier series, and k in gamma star. So f of 0 is what we want, but f of 0 is sum over all fk, because this is 1. So I have to just sum over all fk. So I will just look at the sum over fk. And sum over all k belonging to gamma star. But that's the same as sum over all k belonging to gamma star. And now just compare the two expressions. For y equal to 0, you have that. And now you have accomplished exactly what you were trying to do. Tau bar has gone replaced by minus 1 over tau bar. That was the S transformation here. Right? So you've done that. But in that process, what has happened is that the original lattice sum has gone over to the dual lattice. Right? P has been replaced by K, but K is spanning a different lattice, not the original lattice. It's the gamma star. Okay? So if you want your theory to be invariant, then the gamma star must be equal to gamma. So that means gamma is a self-dual lattice. So these are the two important conditions. The gamma, the p square equal to even, that means this is which is called gamma is even lattice. And this condition tells me that gamma is self-dual lattice. So gamma must be even and self-dual. So this is the main conclusion. And so I just state this and tell you the result. So this is a condition from ordinary invariance, and this is a fundamental requirement. I mean, it is not that if your theory does not satisfy this condition, if it breaks it, the string theory is inconsistent. Okay? You simply cannot develop any perturbation theory, there's no sense. Because this is part of the diffeomorphism actually. It's a global diffeomorphism, which is not connected to identity. Okay? So this implies that gamma 16 is a E1 and self-dual. Now, fortunately, mathematicians have studied this lattice. Actually, more general lattice they have studied. But let me just quote the result here. I mean, in fact, more generally, they have studied lattice. Gamma p comma q lattice, where, I mean, here, see, 16 coordinates are all Euclidean signature. They all had positive signature. But mathematicians have considered more general case, where, say, p of them are positive and q of them are negative. So total dimension is p plus q, where p of them are, it's a Lorentzian type of lattices. P of them are like, say, time-like, Q of them are like space-like, or vice versa. And they have asked the question, what is the, so say this is E1 and self-dual, this condition. But you see, both evenness and circular, these conditions use the norm or inner product of the two vectors. And that inner product is given by this metric. Not the Euclidean metric. Before we are using Euclidean metric. Now it's with this metric. Okay, so with this metric, if something is even circular, and they have the basic theorem is the following. First statement, it exists if and only if P minus Q, modulus of P minus Q is 8 times the integer. Okay? 8 times the integer. This 8 appears in many places, not just in Majorana-Weil condition. Actually, it's related. In fact, it's related to something. 2, two cases. If P and Q, both and P and Q, both are not zero, then there is a unique lattice. Then gamma PQ is unique. Unique in the sense that, of course, up to the, when you have such a metric, you have SOP, Q transformation, Lorentz transformation. Of course, if you give me some lattice and do a Lorentz transformation, is okay. So up to the obvious symmetries. And in the other case,
So if this n is, what is it? Just an integer or?
n is integer, sorry, yeah, sorry, I should have mentioned. So 8, yeah, where n is non-negative integer. N is non-negative. Of course, negative will not make sense. So n is a positive, non-negative. Well, even negative, okay, non-negative. Because I've taken the modulus here. Yes, sorry? Yeah, sorry. C dot?
You should say right Z plus.
Z plus. Yeah. Yeah, but Z plus excludes 0, right? Yeah. Okay, with the 0. So 8 times n, where n can be equal to 0 or n can be equal to Z plus. It belongs to Z plus. Yeah. Okay, so that's that. So actually in our case, actually one of them is 0, since it's not a discrete in this category, right? Because for us, P is equal to 16 and Q is 0, right? So in this case, so suppose Q is 0, and in that case, of course, P has to be equal to 8, or P has to be equal to 16, because it has to be multiple of 8, right? So P must be equal to, if P is equal to 0, it's nothing, zero dimensional. If P is equal to 8 or 16, in this case, the lattice gamma 8 is simply E8 root lattice. And for 16, gamma 16, there are exactly two lattices. So I should just write this here. The gamma 16, there are just two possibilities. A is E8 cross A root lattice. And B, SO30, it's actually more precise in the spin 32 over C2. Weight lattice. What this basically means is that is a SO32 root lattice to which you have added also a speeder plate. Okay, but for our practical purpose, let's think of SO32. It's a SO32 root lattice. I will come back to this. Maybe I'll just mention this as an important point when we talk about dualities. Type 1 heterotic duality. The spinner plays an important role. It was a puzzle for some time as it was solved, I should say. But anyway, so for the present purposes, let's just think of it as SO32 root lattice. And these are exactly, you see, for these two choices, you get those additional massless states. In these cases, the root square, the length squares of the root vectors is exactly equal to 2 in this normalization. This is even lattice, and the length square are exactly 2. And we have seen that whenever you have a p squared length equal to 2, there is a massless state, massless gauge field. So we are saying that for every root vector, in the first case of every root vector of E across E8, you have a massless state, massless gauge field. And similarly, in this case, every root vector of SO32, there's a massless gauge field. So U1 to the 16 is promoted to the E8 cross E8 in the first case, and SO32 in the second case. So notice again this extraordinary thing that from anomaly cancellation, which was a completely different argument. It was not a string theory argument, it was a field theory argument in 10 dimensions. Precisely two gauge groups are picked out, E8 cross E8 and SO32. I mean, to be more precise, two non-abelian groups, E8 cross E8 and SO32 picked out. And in string theory, again, these two are picked out, but it comes from a different root. It is coming from just the consistency of string perturbation. You know, the world sheet theory. Without this modular invariance, the world sheet theory is simply inconsistent. That's the way it appears here. And the same thing with the type 1 string. The reason, the anomaly cancellation of SO32 is seen in the type 1 theory by the requirement that there is no tadpole. Because if there's a tadpole, that means the vacuum is unstable, right? So it's just a requirement that tadpole is absent. Of course, type 1 is a particular example, but when you look at the compactifications and so on, you can have many, many complicated situations, right? But in all of those cases, if you require tadpole cancellation, then the resulting theory is anomaly free in the sense of Green-Schwarz anomaly cancellation and so on. It's not anomaly free in the naive sense, but in a more modified sense. But okay, it's anomaly. It makes it consistent. Time for questions.
Could you please explain again this argument of when you compactify, how do you find this trace? The trace over the Hilbert space? I understand the equation, but how do you...
Okay, maybe I can do it like this. You see, let's think in terms of particle. It doesn't matter whether it's particle or string. If you look at some state, some initial state, and you go over to some final state, with some time t, right? Then the corresponding matrix element will be to the power of minus t in the time for the time state, Hamiltonian times society. Right? This will be the matrix element. But you can. So on the other hand, if I look at now the integration over a circle, path integral over a circle, so we are basically identifying those two states. Right? On a circle, what I can think about, I can sort of break it, right? Break the circle. So I start from here to here, and then identify the 2 points. Identify the 2 points, right? So of course I can, instead of choosing an arbitrary, I can choose a basis of the wave functions, the position basis, right? So I can think of this as an initial xi, initial position, and going to some final position xf into the minus th. This is how you develop the path integral formulation. So you do that, but now you see because I have these two are identified, which means xi is equal to xf, but the value of xi can be anything in this point. So you just get this integral of dx, right? Which going back to the arbitrary, so this is like the trace over the xi's, right? Dx is the integral, which I'm integrating over, taking over all the trace, right? This is the diagonal element of the matrix, and I'm integrating over all the diagonal elements, right? But that is the same for say any other basis. Basis invariant statement would be you just take any basis and evaluate this and that basis and take the trace. That is it.
Any other questions?
In addition to this restriction, it is necessary to impose some restrictions like a Fisher-Sasser mechanism.
What is that?
In order to cancel the divergence of the...
Okay, that would be the case. Let me say I'm not going to that sophisticated situations. Right? So here, I mean, those kinds of things will happen if there are something happens with the higher loops, and then you have to you have to consider vacuum gets shifted because of that. You know? And then you have to recombine everything. Now here, all the vacuum will be stable, so there will be no such problem. No, sorry. Indeed, your question was right. There are more conditions, right? I didn't mention there's crossing symmetry conditions, but that is turns out. I mean, once you have actually, these conditions will also satisfy, will imply that the crossing symmetry is satisfied. Crossing symmetry is already at the tree level. Then you can ask the question, I mean, what happens? I mean, this kind of transformation, as I said, can be thought of as a global diffeomorphism, right? Because one way to think about this transformation is, after all, you are taking this point to that point, right? But that is like, if I look back at the original, picture, which was like this here, and let's say this was one circle and other circle, the two bases for the parallelogram that I've chosen. Now, the tau going to tau plus 1 is like doing the following thing. You cut open, okay? You cut open, twist one side by 2 pi, and then again rejoin. Okay? So it's like a diffeomorphism, but it's not a diffeomorphism which is connected to the identity element. It's a disconnected components of diffeomorphism. So you can do it this way, or you can cut this circle and again open it and twist one side by 2 pi and join, or you can cut some more complicated cycle, like that. So there are all sorts of cycles. You can cut any closed cycles. You can cut, rotate, but this will start becoming more and more complicated, right? If you say go to genus 2. You'll have many cycles there. This cycle, this cycle, this cycle, this cycle, this cycle, whatever. No? So there are all possibilities, and you have this operation. You have many possible such operations, right? You can cut, twist, and then join. These operations are called Dehn twists. These are called DEHN twists. And basically, the modular group is generated by these Dehn twists. So you may imagine. I mean, in fact, it's a very natural question. Is it enough? I mean, we have just checked that at the one loop, it is modular invariant. How do I know it's modular invariant? 2 loops, 3 loops. One has to check. If one has to check each loop by loop, we are finished, right? We cannot do it. I mean, it's impossible. But there are theorems in the late 80s. There are a series of papers by, I think, Greg Moore and Cyber. I think there are two papers at least. Or maybe it's one, maybe just very fast. So where they show, so they give the necessary and sufficient conditions, which ensures modular invariance at all loops. And that condition, if I remember correctly, was crossing symmetry and one loop modular invariance of one point function, not just the partition function of one point function. But that guarantees that the theory is modular invariant to all loops. And this, at the moment I have only showed that this is a necessary condition, but it turns out this is sufficient for the hadronics, for all loops.
Okay, let's thank once again.